May-June 2022, variant 3.5. Finding the value of X in basic copper to carbonate by measuring the volume of carbon dioxide collected. Quantitative analysis question says, read through the whole method before starting any practical work. Where appropriate, prepare a table for your results in the space provided. Show the precision of the apparatus you used in the data you record. Now, the precision means you have to record every observation, every volume, every mass, every temperature, up to the error of the device. It is called the precision of the apparatus. Show your working and appropriate significant figures in the final answer to each step of your calculation. Appropriate significant figures means minimum 3 significant figures, and for better calculation, it must be 4 significant figures. Now, question says, basic copper 2 carbonate contains both copper 2 carbonate and copper 2 hydroxide. The ratio of these two components can be different in the samples from different sources. This means that the formula of basic copper 2 carbonate can be written as copper carbonate is just taken as 1 mole, but copper 2 hydroxide is taken as X moles. So the ratio is different. So this is 1, then it must be something. Both the carbonate and hydroxide reacts with the acid according to this equation. You will determine the value of X in the sample of basic copper 2 carbonate by reacting it with the excess acid and measuring the mass of carbon dioxide given off. Fa1 is basic copper 2 carbonate and Fa2 is 2 molar hydrochloric acid. Apparatus and chemicals given are: Fa1 is a green solid in a test tube with rubber bung. Then Fa2 is an aqueous solution, conical flask, and a 25 centimeter cube measuring cylinder. Method: use 25 centimeter cube measuring cylinder to transfer 25 centimeter cube of Fa2 into the conical flask. Using this 25 centimeter cube of measuring cylinder, transfer this Fa2 25 centimeter cube into the conical flask. So here it is, 25 centimeter cube taken, and transfer is into the conical flask. Next step says, weigh the flask with acid, record the mass, and weigh the container with Fa1, record the mass. So let's measure both masses now. Now measure the mass of flask with the acid. Mass of Fa1 with container. So both masses are recorded as 155.57 and 29.45 grams. Now, carefully tip all the Fa1 into the acid in the conical flask. Swirl the contents of the flask and leave the flask to stand. Meanwhile, weigh the container with any residual Fa1 and record the mass. So let's do it now. Tip all the Fa1 into this conical flask. And shake the flask for the reaction to happen. As we can see, fizzing is happening. A lot of gas is released, means carbon dioxide is forming. Swirl the flask and leave the flask to stand for some time so that the reaction gets completed and all of carbon dioxide gets evolved. It has taken approximately 3 minutes to get this reaction completed, and now there is no more fizzing happening. So the reaction is completed. Now let's take the mass of container with any residual Fa1. So the mass is 2729. The weight of container with any residual Fa1 is 27.29. The next part says calculate and record the mass of Fa1 added to the flask. Now I can take out the mass of Fa1 by subtracting the masses of container with Fa1 and without Fa1. So subtracting these two values, I will get the mass of Fa1 used in our experiment, and that is 2.16 grams. Next point says calculate and record the theoretical initial mass of the flask and acid and Fa1. Now this can be calculated by adding these two masses. Initial mass of flask and acid is here. Mass of flask and acid is here, 155.57, and the mass of Fa1 added is above 2.16. So once we add these two values, we will get the theoretical initial mass of the contents of flask, which is 157.73 grams in this case. Now the next part says swirl the flask occasionally, weigh the flask and the contents after approximately 5 minutes, record the mass. Now let's take the mass of the flask with the acid content remaining. Now the recorded mass of content of the flask after the reaction has finished is 157.25 grams. The next part says calculate and record the mass of carbon dioxide given off during the experiment. It means firstly we have recorded the mass initially, theoretical initial mass of the flask and the acid NFA1, and then we have recorded the mass of the flask, any residual acid and the Fa1 consumed after 5 minutes. It means this is the mass after the reaction has finished, and this was the total initial mass when the reaction was started. So if we subtract these two values, we will get the mass of the gas released and the mass of carbon dioxide given off. So let's subtract these two values now. So the mass of carbon dioxide given off by subtracting these two values is 0.48 grams. Now, we have to record all our results. We have recorded here in the form of a proper table. So let's make the table now in this space given below with 4 marks. So all the masses are recorded in a proper table here. And now move on to the next part, which says parts B, calculations. Calculate the amount in moles of carbon dioxide given off in the reaction. Now to calculate the moles, we have a formula of moles is equals to mass in gram divided by mR. So in this case, the mass given of for carbon dioxide in the table was here 0.48 grams of carbon dioxide was given off. So the mass given off here is 0.48 divided by the mR of carbon dioxide is carbon is 12 and oxygen is 16 times 2. So 44. If we divide this 44, we will get 0.0109 up to 3 significant figures, the moles of carbon dioxide given off. Now the next part says calculate the amount in moles of copper to carbonate present in the sample of Fa1 that you added to the flask. Now from this part of carbon dioxide, we can relate that In a previous page, equation for the reaction of acid with copper to carbonate was given. In the equation, copper to carbonate forms carbon dioxide in 1:1 ratio. Therefore, in this part, when carbon dioxide is 0.109 moles formed, it means copper to carbonate will be in the same amount. So 0.0109 moles of carbon dioxide will be given off with the same moles of CuCO3. So 0.0109 moles of CuCO3. Now the next part says, hence calculate the mass of copper to carbonate in the sample of Fa1 that you added to the flask. Now from the moles of copper to carbonate, we have to calculate the mass. Again, the same formula. We will put moles here, 0.0109 moles of copper carbonate. And we need to calculate its mass in gram divided by the MR of copper to carbonate, which is 63.5 for copper. Carbon is 12 and oxygen is 16 3 times. So here, if we calculate, the mass is 1.346 grams of copper to carbonate. Part 3. Calculate the mass of copper to hydroxide in the sample of Fa1 that you added to the flask. Now we have the total mass of Fa1 on the previous page, that is 2.16. And the total Fa1 contains two substances, copper to carbonate and copper to hydroxide. So if we write here 2.16 is the total, which means copper to carbonate and copper to hydroxide, the total is 2.16 grams. And out of this total, we have copper to carbonate calculated here as 1.346. So what is the amount of copper to hydroxide? So we can calculate by subtracting this value from this 2.16. We will get the mass of copper to hydroxide. So 2.16 minus 1.346, it will give you 0.814 grams of copper hydroxide. Now moving on to the next part, it says calculate the amount in moles of copper to hydroxide in the sample of Fa1 that you added to the flask. So we have got the mass in gram of copper hydroxide and we need to calculate its moles. So again, the same formula, moles is equals to mass in gram, which is 0.814 grams this time, divided by the MR of this copper to hydroxide, which must be 63.5, and twice of 16 and 1 hydrogen. So altogether it will give us 0.00835 moles of copper to hydroxide. Now let's move on to the next part. Says hence calculate the value of X in the formula of basic copper to carbonate. Now if the formula says the copper carbonate and copper hydroxide are attached in 1, here is 1, in is to X ratio. So the calculated moles above we got are 0.00835 for copper to hydroxide, and the copper to carbonate moles we calculated in the first part was 0.0109. So here if we write 0.0109, we can calculate the X. Now the X here is 0.766, which is approximately equals to 1. So the value of X here is 1. Now moving on to the next part, which says In this determination, you assume that hydrochloric acid is in excess. By calculation, show this assumption. So if we want to calculate the total moles of hydrochloric acid added in the flask, we need to look back at the first page saying the concentration of hydrochloric acid we have taken here was 2 moles per dm cube, and we have taken Fa2 25 centimeter cube volume. So 2 moles per dm cube and 25 centimeter cube volume is used to calculate the moles here. We can see moles of HCl added is equals to concentration 2.0 multiplied by 25 volume upon 1000. So the added moles are 0.0500. So these are the moles of HCl added. Now if we look at the moles consumed, it means if we look at the equation on the first page, copper to hydroxide and copper to carbonate both have used the hydrochloric acid in 1:2 ratio. It means the moles of copper to carbonate we got and the moles of copper to hydroxide we got. We will double them to get the moles of hydrochloric acid used. So the moles of copper to hydroxide we got here are 0.00835 and the moles of copper to carbonate we got 0.0109. So if we multiply together these two values by 2 will give us the moles of HCl consumed. So if we calculate the total moles consumed are 0.0385 moles consumed. Now if we look at the moles which are consumed and the moles which are given, which are added, so added moles are actually greater. So 0.0500 is greater than the 0.0385 moles of HCl. Therefore, it is used in excess. So here we comes to an end of 10 marks gravimetric question of May-June 22 3-5 variant.